Okay, good morning to all of you. So yesterday we were doing convolutional codes. Let me briefly uh, go through these codes and go through what we covered last time, and then I will proceed further. All right, let me do the slideshow and let me check whether okay. So convolutional codes. So the convolutional codes can be specified using n comma k, small k and capital K. Small n is the number of bits in the code word. Small k is the number of bits in the message vector. Capital K is the constraint length. Constraint length is dependent on the number of elements in the shift register, right? Number of memory elements in the shift register. So if number of memory elements in the shift register are 2, constraint length will be 3. So number, if let's say in general number of elements in the shift register are k minus 1, capital K minus 1, the constraint length will be k. Code rate is defined as number of message bits divided by the number of code word bits in the code word. All right, so this diagram I explained that how the information vector will go into the convolutional encoder and the codes will be generated, right? Then at the demodulator side, the signal is demodulated and this received sequence needs to be decoded because we have encoded it using the convolutional encoder. Now we need to decode it also, and then we will make an estimation of the message bits that were used to encode, and then we will do the decoding and we'll estimate the message bits, right? So this is the example that I took to explain the convolutional encoder. I explained you yesterday also very stressfully. I explained that there are three boxes in the shift register, but only 2 boxes refer to the memory element. The first box is for the input, right? So the constraint length of this convolutional encoder will be 3. 1 bit. So how many bits will go into the input? Only 1 bit I'm considering, and 2 bits are coming as the output. So rate of the rate of this encoder is 1 by 2. All right. Then I took the message vector as 101. So 1 by 1, this 101 will go into the shift register, and we will get the output. So assuming that the 2 bits in the shift register are 0, 0, and when 1 comes, right? So what is the XOR gate for XOR output of the first case, first generator polynomial 1, 1, 1. So the output is 1. That means U1 is 1 and U2 is 1 again. Right. Now this one, for the next time, 1 moves into the second position and the next input bit is 0. So again we will do the XORing and to find out the branch word. So one time this U1 and U2, small U1 and U2 are known as the branch words. This is first branch word, second branch word, third and fourth and so on. So you need to flush the 101 vector, message vector out of the shift register. So for that you need to push zeros into the shift register. So ultimately, when all the boxes in the shift register become all zeros, then what is the, so message vector was 101. This is the code word that you will receive 11100010 and 11. Up to this dotted line tells us that these 5 branch words will come, and the final and the last stage and the final stage will be 000, and the code word generated is 11100010 and 11. This is how the encoding is done, right? So let us say if capital L is the number of data bits in the encoder that we are considering, that means small k is equal to 1, which basically means capital L equal to 1. So in that case, the effective, actually the code rate defined is 1 by 2. Here from the structure of this convolutional encoder, because 1 input bit will go inside the shift register and 2 output bits will come. That means n is 2 and small k is 1. So therefore rate of the code as is seen from this convolutional encoder structure, it is 1 by 2. But what is the effective code rate? Effective code rate is if 3 bits we are sending in, we are getting 10 bits out. So 3 by 10 is the effective code rate. So effective code rate is different from the structural code rate. Now, what is the effective code rate? Effective code rate in general for a convolutional encoder is given by capital L divided by N, number of bits in the code word, capital L plus K is the constraint length minus 1. And this will be less than RC, the actual code rate. As you can see, this code rate 3 by 10 is less than 1 by 2. From the structure, the code rate is 1 by 2, which is RC, and effective code rate comes out to be 3 by 10. So that's why the effective code rate is less than RC. This is the general formula for the effective code rate. All right. Then this is the vector representation that I discussed last time also. Vector representation means how the connections are being made from the shift register and the input to the XOR gates. So all this is 1, 1, 1, indicating that this connection is there, this connection is there, this connection is there. But for the second generator polynomial, it is 1, 0, 1. So it is 1, no connection for the second box, second memory element or a flip-flop. The third box will go, so it is 1, 0, 1. And we can express the encoder using these vector representation also. G1 and G2 are the vectors which show the connections going into the XOR gate. And we can also represent using the polynomial representation. So G1 was 1, 1, 1. So 1, 1, 1 means the polynomial will start from the constant, which is 1 plus x square plus x cube plus x4 and so on. But only 3 connections are there for G1. So it will be 1 dot x plus 1 dot x square. Take the coefficients out, that will be the vector notation 1, 1, 1. So this is how we can express it in terms of the polynomial representation also. But for the second case, the coefficient it was 1, 0, 1. That means the coefficient for x is 0. So therefore it is 1 plus x square. So by looking at the polynomial itself, we can say that all the 3 connections going into the XOR gate, and looking at this polynomial 1 plus x square, we can say that 2 connections are going into the XOR gate. And we can so what was the message vector? Message vector was 1, 0, 1. So the polynomial representation of 1, 0, 1 is 1 plus x square. G1x, which is the first generator polynomial, it is 1 plus x square. We can multiply it. For the second case, we can also multiply 1 plus x square plus 1 plus x square, we'll get 1 plus x4. Then we add these terms and we take the 2 coefficients out. Not add, we take mx g1x separately, mx g2x separately, and whichever term the coefficient for any term, if it is 0, we will put the coefficient there, and we take the coefficients out. 1, 1 is taken here, 1, 0 is taken corresponding to x, 0, 0 is taken corresponding to x square, and so on. So this is the code word which we obtained using the using this structure, doing the XORing also, and we can solve it using the polynomial mathematics also, and we will get the same code word for the same message vector if we use G1 and G2 as 1, 1, 1 and G1 as 1, 1, 1 and G2 as 1, 0, 1. Right. Then I also explained you that the encoder can also be represented using a finite state machine. Then I explained what you mean by the state of the encoder. The state of the encoder is defined by the 2 memory elements. I repeat once again, the first box is only for the input. These 2 are the memory elements. The contents of these 2 memory elements will define the state of the encoder. So 2 bits will be there. So that means the encoder can be in 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. I represent these 4 states as S0, S1, S2, and S3. So I can put the convolutional encoder in the form of a state diagram, meaning by I will see, assuming that firstly the encoder state is 0, 0, right? And if 1 comes, what is the next state and what is the output. If 0 comes, what is the next state and what is the output. This is how we represent using a state diagram. Okay, let me show you the state diagram here. Okay, so if the initial state is 0, 0, if 0 input comes, the output will be 0, 0 and it remains in S0 only. But if the initial state is 0, 0, input bit 1 comes, next state will be 1, 0 and the output will be 1, 1, right? And now let us look at this state. If 1, 0 is this initial state, if 0 comes as the input, the next state will be 0, 1 and the output will be 1, 0. If 1 comes as an input bit, next state will be S3 or 1, 1 and the output will be 0, 1. This is how I think you must have gone through these state diagrams in your digital electronics course also. So what I mean to say is that convolutional encoder can be represented using a state diagram also. There is a problem with representation using a state diagram. What is the problem? The problem is that the state diagrams do not incorporate any timing information, right? For example, if the encoder state is S0 at time T1, at time T2 it is S1, at time T50 it is let's say S3, but we cannot, from the state diagram, we cannot tell that what was the state of the encoder at time T100 or T50 or T70. State diagrams do not contain timing information. They can tell you what is the output and what is the next state, right, depending on the input bit, but they cannot tell you at what time what was the state of the encoder, what was the output. Now, to incorporate timing information into the representation, we use a diagram which is called a tree diagram. How the tree is made, for drawing these outputs, for writing these outputs, I'm using the same encoder. Same encoder means where G1 was 111 and G2 was 101. Based on that, the outputs are being written. Now, how the tree diagram is drawn. When input bit 0 comes, we have to move upwards. When input bit 1 comes, we have to move downwards. Now, let's say the initial state is A and an input bit 0 comes. So that means we have to go upwards. What is the output? 0, 0. And what will be the next state? Next state is A only. But if the initial state is, if the previous state is A, but input bit 1 comes, what will be the output? 1, 1. What will be the next state? B. As I said, I have taken this diagram from Burnett's Clark book. Here A is actually means S0 state, B means S1 state, C means S2 state, and D means S3 state, right? So in that book, it was written, the states were represented using A, B, C, D, but in my previous slide, the representation is done using S0, S1, S2, and S3. Now, again, you go on drawing the tree diagram. If the initial state is A again, the output is 0, 0, the next state is A only. But if it is 1, because when I move downwards, it indicates that input bit was 1. So output, when initial state is A and the input is 1, the output will be 1, 1, and the next state is B. From here, if you go for each state, writing the outputs and the next state, the tree diagram will continue till the end. Till the end means it can, if let's say there are, I am looking for 500 times or 1000 times or 2000 times, you can very well imagine that though it contains the timing information, the representation contains the timing information, but the problem is that it is growing exponentially. The tree diagram, it's very difficult to draw first of all, and then even to implement a tree diagram like this, it's very difficult. Now, what we can look at from this tree diagram, after the constraint length, please remember, after the constraint length, what is the constraint length of our decoder? What was the constraint length? It was 3. That means after 3 time periods, this is 1, this is T1, this is 2, and this is 3. After the constraint length, which is defined as, which is taken as a time period, that means 3 time intervals, you try to look at the tree diagram. The upper portion of the tree diagram and the lower portion of the tree diagram are identical. This is A, B, C, D on the upper half, A, B, C, D on the lower half. If you go further, it is A, B, C, D, A, B, C, D for the upper half, A, B, C, D, and A, B, C, D for the lower half. So you very well can look at the tree diagram and find out that after the constraint length is over, the upper portion of the tree diagram is the same, is identical to the lower portion of the tree diagram. So what we can do is we can merge the upper portion of the tree diagram and the lower portion of the tree diagram. That means the branches will be merged with each other. Once you merge the branches, the corresponding branches, a new structure takes the shape, and that structure of representation is known as the trellis diagram. So let me show you the trellis diagram. So this is the trellis diagram. Now, how the trellis diagram is made. Let me explain the trellis diagram using this slide. Now, this is very important because in your assignment also there are questions based on this. Very important from the examination point of view also. Some question may be on linear block codes, and modular. I mean, there can be an important question there, right? So this is very important actually to understand the trellis diagram. So let me explain it. In the encoder, I'm using the same example of the encoder. What is the encoder that I'm referring to? I'm referring to this encoder. This is the structure of the encoder that I'm referring to. The same encoder I'm using. The U1 and U2 will be calculated according to this structure. All right. So let me come to this trellis diagram. So I am using the same encoder and I will draw the trellis diagram from that. So how many states are there in the encoder? There are 4 states, S0, S1, S2 and S3. Why S2 is put here? Just because you can put any state here. It can be S4, S3, S2. It can be S0, S2. Because in the state diagram, if you see, the first movement from S0 is towards S2. Or you can represent this S2 as S1. So that will not change the trellis diagram. Anyway, either if you call whatever S2, if I'm calling this state as S2, you can call it this state as S1 or S3, right? So because the first movement is from S0 to S2, that is why it is taken like this. Otherwise, there is no binding on whether you call it S1 or S3. The structure only will change, I mean, in terms of the states. Otherwise, the information remains the same. All right. So let's look at the states. How many states are possible? 4 states are possible. 0, 0, 1, 0, 0, 1, and 1, 1. 4 states are possible. Now, if you see, let me come to this diagram. I think this, so 4 states are there. To draw the trellis diagram, to start with, first make 4 dots. This black one, black one, and black. 4 dots are made, and these dots are represented with the states 0, 0, 1, 0, 0, 1, 1, 1. You can represent other way around also 0, 0, 1, 1, 1, 0, 0, 1. Anyway, you can represent, there is no problem. But let us concentrate on this representation that I'm showing in this slide 0, 0, 1, 0, 0, 1, and 1, 1. So let's come to this slide. So 4 dots, and the first dot corresponds to 0, 0, the second dot corresponds to 1, 0, third corresponds to 0, 1, and fourth corresponds to 1, 1. So this is how the 4 dots are drawn. Now, if you start from the first dot on the top of the 4, you will see that there are two colored lines drawn. Here actually this slide is making the distinction using two ways. One is it is using color also. The other distinction it is trying to make is with a bold line and a dotted line. Since when we will draw on the copy, we will not use the colors, right? Only thing is that either you will put a bold line or a dotted line. So what is the difference? When the input bit is 0, when the input bit is 0, the going from this previous state, this dot to next dot, that means the previous state to the next state is represented using a bold line when the input bit is 0. In this slide, it is I am representing it with a bold line also and the colored line also. You can use both if you have two colored pens, but that does not make any difference. Either you can put a bold line for a bit, for an input bit to be 0, and a dotted line for an input bit to be 1. So this state is, let me come to the previous slide. I think I can explain from here. These states are 0, 0, 1, 0, 0, 1, 1, 1. 4 dots are drawn to represent the 4 states. The bold line is drawn when the input bit is 0. The dotted line is drawn when the input bit is 1. So, assuming that the initial state is 0, 0, and if 0 comes as the input bit, if 0 comes as the input bit, what will be the output? The output will be 0, 0. So this is how the representation is done. 0 obliques double 0. 0 in the numerator indicates what is the input. 0, 0 in the denominator indicates what is the output. Now, if you look at the encoder structure, when the input bit is 0, so all the 3 contents will be 0, 0, 0. What is the output? Output will be 0, 0, 0. So let me come back to the trellis state. So when the initial state is 0, 0, input bit is 0 and the output bit will be 0, 0. And the next state remains 0, 0 only, because for the next state at time, this is at time ti, this is at time ti plus 1. These 4 dots at ti plus 1 again represent the 4 states. This is the previous state and one of them will be the next state. But if the input bit is 0, it will go from 0. The previous state is 0, 0. The next state will also be 0, 0. Right? So that is why the bold line is drawn horizontally and connecting these 2 dots only, indicating what it is indicating. It is indicating that even if I don't write here, again, I mean output I will have to write, but I cannot, if I don't write the numerator part, it is a self indication because I'm using a bold line which tells me that 0 was given as an input. What is the output? Output is 0, 0. I can only write 0, 0. And what is the next state? Next state is 0, 0. But if the input comes as 1, what is the next state? Next state will be, what will be let me show you the next state also. Okay. If the input bit comes as 1, first of all, look for the output. Before looking for the next state, look for the output. So when the input bit is 1, what is the output? The output is 1, 1, of course. And what is the next state? How do we find the next state? You will have to move this 1 further at the second position, and this 0 at the second position will go to the third position. The third position 0 will go out. That will be the next state. So the next state will be 1, 0. This 1 will come, this 1 at the first position will come at the second position, and the 0 at second position will come at third position. So now let me come back to the trellis and I will show you that if the previous state was 0, 0, but input bit is 1, what is the output? The output is 1, 1. But what is the next state? The next state is This dotted line is connecting the first dot in the for the TI time, and it is connecting to this dot. This dot is representing which state? 1, 0. Right? So this is how the trellis diagram is plotted or developed or drawn for all the states. Now look, now let us consider the cases for 1, 0. If the initial state is 1, 0, if 0 comes as the input, what is the output? The output will be 1, 0. And what is the next state? If 0 comes as the input, what is the next state? Next state will be 0, 1. So it goes this line, this red line where my cursor is moving, this is telling me that input bit was 0. How it is telling me? The line is bold and line is with a different color, red. So this is telling me 0. And what is the output? Output is 1, 0. Since I am connecting this dot with this dot, previous state was 1, 0, next state is 0, 1. So this is how all the states, for all the states, the trellis diagram is completed. Right? Now let me come to this point. This first portion going from T1 to T2 is whatever is drawn here. Now, in the same way, you have to go from these. So these dots represent the same states, S0, S2, S1, and S3. Right? If you go from T2 to T3, again the same procedure. Going from T3 to T4, again the same procedure. T4 to T5, again the same procedure. T5 to T6, again the same procedure. Right? So for how many times we have to move forward? The input data was 101, and we need these two tail bits to flush out this data, flush this data out, right? To get the 5 code words. The code words are, the branch words are 11, 10, 00, 10, and 11. So this is my code word for 101. But I have to draw the trellis diagram for all the states. And mind you, the transmitter, of course, knows the encoder structure. If the encoder structure is known, I can draw this trellis diagram. And trellis structure is also known to the receiver, because receiver knows what structure of the encoder is present at the transmitter. Transmitter can be in Patiala, receiver can be in US. Both the transmitter and receiver know what is the type of, what is the structure of the encoder, right? So this trellis is known. This is the trellis, this is the full trellis, which is known to the transmitter also and the receiver also. Correct? Now, the question is that, let me, before I explain all this, let me show, okay, let me just take this as the first 3 lines are in this slide. The input is 101. The code word that is formed by the convolutional encoder is 11, 10, 00, 10, and 11. We have already seen it. So this is transmitted. I'm considering one transmitter at Patiala and receiver at, let's say, Texas. So from Patiala, this code will be transmitted. At Texas, you receive this code word 11, 10, 11, 10, and 01. I don't know whether this is the correct code word or not, because I don't know what was the only transmitter. At the transmitter, these message bits are appearing. Message bits are not appearing at the receiver. Receiver receives only this data 11, 10, 11, 10, and 01. But receiver has no idea whether while traveling from Patiala to Texas, any error has occurred or not. I cannot take whatever is received at the true data. I need to, first of all, I need to decode it. And at the same time, I need to correct the errors also if any error has occurred. So what is the procedure? This is the received code word. How can I know whether this is the correct received code word? And from the received code word, I need to decode what was the message vector. How can I do? These are the branch words 1110 1110. So I will have to how many bits are there? 10 bits are there, right, in the code word, and I have received 10 bits. So 10 bits, how many combinations of 10 bits are possible? Combinations of 10 bits which are possible is 2 raised to the power 10. I have to compare this received code word with every possible code word. And I need to compare how? I need to match ones and zeros at different bit positions, which I call as the distance between the two. And I will assume that the received code word is actually for whatever the possible combinations of the code words, and the comparison with the received for whatever possible the comparison of the received code word. How many possible combinations are there? 2 raised to the power 10. Received code word will be compared with 2 raised to the power 10 code words possible. Wherever I will find the distance as the minimum, I will assume that actually that code word was transmitted. Right? So in this way, how many comparisons I will have to make? 2 raised to the power 10. But here only I am considering message bits to be 3 bits only. But let us say I consider a message block of 1000 bits. And a code word approximately comes out to be, let's say 50 bits. How many and 50 bits are received at the receiver? I don't know what is the possible code word. So I will have to compare in that case the received code word with 2 raised to the power 50 code words, which is a humongous task. And this approach is known as brute force approach, which is not possible practically to estimate what is the actual code word that was transmitted based on the received data. So this is not possible. The brute force approach cannot work practically. So what is the solution? The solution was proposed by Andrew Viterbi, and this algorithm was proposed in 1967. So Andrew Viterbi is the same person who actually founded the Qualcomm company. He is the founder member of the Qualcomm. He actually laid the foundation of Qualcomm. And in USA, in universities, there are many schools. One school I know, it is the Andrew Viterbi School. In 1967, he gave this algorithm, right? And he did not publish the algorithm, rather he did the patent for this. And if I tell you, this Viterbi algorithm is used presently also in all the 5G, 6G communications. And because of this algorithm, the systems, it has been possible to develop systems, because as I explained to you, brute force approach is almost not possible. Andrew Viterbi gave an algorithm in 1967 Based on this algorithm, what he tried to do is that it reduces the decoding complexity to L times 2k minus 1. Let's not go into this figure. The important point is that the Viterbi algorithm reduces the computational complexity to a great extent. So what is Viterbi algorithm? The Viterbi algorithm performs maximum likelihood decoding. It finds a path through the trellis. I have already explained you what is a trellis, which is known to the receiver also and transmitter also. But which data was transmitted? It is important to note that. So because there are many, I will explain this algorithm. It finds a path through the trellis with the largest metric. I will explain you. Okay. So probably today I will not be able to complete this algorithm. I will leave this explanation of the algorithm for the next class because this is an important topic. So the important point that I would like to make here is that Viterbi algorithm is used to reduce the computational complexity, which appear to be huge if we use the brute force approach, right? So this is the algorithm, algorithmic steps, but I will explain you from the diagram and will tell you how to decode the data, right? So let me briefly start the example and then I will take over this example once again tomorrow. What is given to us as an example or practically also? We will receive some at the receiver. We have to actually know what is the message vector that was sent. First of all, we need to know what is the code word that was sent. And then from the code word, we want to know what was the message contained in it. But what we have received, this code word was transmitted, U was transmitted, but what we received was Z. This code word was received. We don't know whether it is correct or not, because here I am taking the example of only 3 bits, but in real-time example, continuously thousands, millions, billions of bits are traveling as digital data. So it is impossible to know at the receiver what data is being transmitted, right? So at the receiver, we have to actually decode and estimate the data. For that, we need to use either we can use the brute force approach or we can use the Viterbi algorithm. The problem with brute force approach is that the computational complexity is huge. Now we need to use the Viterbi algorithm. So what is received? Received is 11, 10, 11, 10 and 01, right? So how to decode it and how to know that this code word was transmitted and this message was transmitted. We have only Z at the receiver, but we know the structure of the encoder that is being used at the transmitter. That means we know the transmitter trellis. This trellis we know. This trellis we know. That the encoder has got what is the structure of the encoder, how the connections are made, right? And what possible states can the encoder be in, and what possible outputs can be there. We know this much of thing, right? So receiver knows this trellis. Now the question is that this is received. From here we want to know what was transmitted. We will start developing the trellis at the receiver. Now let's look at how to do that part. So this is done like this. We will start from here, assuming that the initial state was 0, 0, because we will assume at the receiver that initially it was 0, 0. Now, what is received as a first branch word? The first branch word received is 1, 1. This is the transmitter trellis. This is the in general trellis. Received is 1, 1. Let's look at this branch going from state 0, 0 to state 0, 0. the output is 0, 0 if the input bit was 0. But what is received here? It is 1, 1. What is the output? If had the 0 been had it been 0 as the input, the output would have been 0, 0. But here the output is 1, 1. What is the distance between the two outputs? It is 2, because it is differing from each other by 2 bit positions. Right? So we will write the distance here. It is 2. Now, what is the output? It is 1, 1. But if 1 was transmitted, what is the output? Output is 1, 1. So now what is the distance between 1, 1 and this 1, 1? It is 0. So what we put here 0 as the distance. So this distance is going from this state to this state, the distance is 2. Going from this state to this state, the distance is 0. These distances are known as the branch metrics. These going from one state to the other state, this distance is known as branch metric, or this is also known as the Hamming distance. Okay, I will continue with the rest of the Viterbi algorithm and what is Viterbi algorithm, how the decoding can be done, and I leave it to the lecture tomorrow, for the lecture tomorrow, and then we will finish with the Viterbi decoding. If any questions are there till now, what I have covered, please ask if any questions are there. So in the exam, you will be given you may be given an encoder structure, right? Sorry. You will be given the encoder structure and you will be given this Z. And you can be asked to decode this received code word. So tomorrow we will see how the Viterbi decoding will be done. If any questions are there, then please ask. Or I will end the lecture and we will meet tomorrow to finish this convolutional codes part. Okay, thank you very much for joining. We'll meet tomorrow.